we know that let V be any vector space and W is non-empty subset of V, then W is called subspace of V if W is closed under, that is W1 bar plus W2 bar belongs to W, and K times W1 W bar or W1 bar belongs to W, where K is any scalar, K is a scalar, and W1 bar and W2 bar any two elements of any two elements from set W. In last lecture we have discussed the intersection of two subspaces, okay, is again a subspace in a subspace. So but what about union of two subspaces? So union of two subspaces, union of two subspaces may or may not be subspace of vector space V. For example, if we take, say here, let V is equal to R square, okay, with usual addition and scalar multiplication, and if we take a set W1 is equal to collection of all x0 where x belongs to R, and W2 is equal to collection of all 0y where y belongs to R, then we know that is in W1 y coordinate is 0 and in W2 x coordinate is 0. Then as we know that W1 and W2 are subspaces of V. Why? If we take any two element, for example, I am going to show here W2 is a subspace. Now what is the W2 here? W2 is equal to collection of all 0y where y belongs to R, okay, real number. Now if you take vector W1 bar is equal to, say, 0y1 and W2 bar is equal to, say, 0y2. If you write some element of W1, you can see it is a 0 1 0 2, then 0 0 0 minus 1 and so on, whose x coordinate is what? 0. So if you take any two vectors from W2 where W1 bar and W2 bar lies in set W, then their vector addition W1 bar plus W2 bar is equal to 0y1 plus 0y2, which is equal to 0 plus 0 0 and y1 plus y2. So this lie in the set, this belongs to set W2, and therefore it is closed under vector addition. Similarly, if we take any scalar k, W1 bar, that is equal to k times 0y1, which is equal to 0 times ky1, and it again lie in set W2, and therefore W2 is a subspace. This implies, and W2 is non-empty also. Why W2 is non-empty? Because there exists at least one element. Which element? Say 0 0 lie in set W2, and therefore W2 is what? Non-empty, and therefore W2 is subspace. W2 is what? Subspace. Now it is a subspace. Similarly you can show that W1 is also subspace of V. Now but if you take the union of these two subspaces W1, if you take first intersection W1 intersection W2, so W1 intersection W2 contain only 0 bar, which is equal to 0 0, and it is a trivial subspace of V, is a subspace of V is equal to R square. This is what? Trivial subspace of any vector space R square. But if you take the W1 union W2, it is not a subspace, Why subspace? Because if we take elements, say 2 0 lie in W1 and W1 union W2. Say since 2 0 lie in W1 implies 2 0 belongs in set W1 union W2. What is union? Means what? It must lie either in set W1 or set W2. Similarly, 0 2 lie in set W2, belongs to in set W2. Then 0 2 belongs in union W1 union W2. Okay. Now, but their addition 2 0 plus 0 2, which is equal to 2 2, does not belongs to set W1 union W2, and therefore it is not W1 union W2 is not, therefore W1 union W2 is not close under vector addition, and therefore W1 union W2 is not subspace. But what is the condition so that the union must again a subspace of V? So for that I am going to write here one theorem. Let W1 and W2 to be subspaces of vector space V, space V. Then W1 union W2 is subspace of V if and only if either W1 is a subset of W2 or W2 is subset of W1. Now we want to prove this. That is, what is the condition so that W1 union W2 is a subspace? Either W1 is what? Either W1 is a subset of W2 or W2 is a subspace of W1. So we are going to prove this. Now to first we are going to prove here. First we are going to prove here then part that is given. What is given here? Given W1 and W2 subspace space of V, and W1 union W2 is subspace of V. And what is our claim here? We claim that either W1 is a subset of W2 or W2 is subset of W1. So first we assume that. Now prove. Now suppose, now if W1 is subset of W2, then proof is trivial. Proof is complete, or you can say that here trivial. But if W1 is not subset of W2, then we want to prove that W2 is a subset of W1. Now since W1 is not a subset of W2, now how to show that A is a subset of B? If there is some space, I am writing here. Okay, how to show that A is a subset of B? I am writing here. Now to show that A is a subset of B, if X belongs to set A, then X belongs to set B, then we can say that if for every element in set A is an element of set B, then we can say that A is a subset of B. So this is the condition. If X belongs to set A and if that element lie in B, then we can say that A is a subset of B. So here we are going to same logic to show that. What we want to show that here W2 is a subset of W1. Okay, why? Because W1 is not a subset of W2. Now since W1 is not subset of W2, this implies there exists an element U bar belongs to W1 such that U bar does not belongs to set W2. Okay. Now since U bar belongs to W1, this implies U bar belongs to set W1 union W2. By using definition of union, let V bar belongs to W2 be any element. Now this implies V bar belongs to W1 union W2. Again, by using definition of union, here you can say that definition of union for these two statement. Okay, here U bar belongs to W1 implies U bar belongs to W1 union W2. Now what is given? Given, you can check here, given W1 union W2 is a subspace of V, implies it is closed under vector addition. Now since I am using a different color, okay, now since W1 union W2 is a subspace, given subspace implies U bar plus V bar belongs to W1 union W2. Okay, so this implies this U bar plus V bar belongs to W1, or U bar plus V bar belongs to W2. Either it line said W1 or W2, but U bar plus V bar does not belongs to set W2. Why? Because suppose if U bar plus V bar belongs to W2, then now since what is here, you can see here V bar belongs to W2. Now since V bar belongs to W2 implies minus V bar belongs to W2. Why? Because here, because W2 is a subspace. So if V bar belongs to W2 implies minus V bar is also belongs to W2, and if U bar plus V bar belongs to W2, it implies U bar plus V bar plus minus V bar is also belongs to W2. Because why? Here again W2 is a subspace. Now by using associative property, you can write this as U bar plus V bar minus V bar belongs to W2, but this implies U bar plus 0 bar belongs to W2, and this implies U bar belongs to W2. But which is contradiction? What is contradiction? You can check here. What we assume here I am highlighting. Okay, I am highlighting here U bar belongs to W2. Which is U bar does not belong to W2. Okay, so it is a contradiction, and here we get U bar belongs to W2. Why we obtain this? Because we assume here wrong. Okay, so what this implies, why we obtain this contradiction, which is contradiction that U bar does not belongs to W2. So what this implies, and therefore U bar plus V bar does not belongs to W2. Now U bar plus V bar does not belongs to W2 implies U bar plus V bar belongs to W1. Now U bar plus V bar belongs to W1. Now since V bar belongs to W1 implies V bar minus V bar is also belongs to W1, and W1 here why it is again, since W1 is a subspace, so it is itself a vector space. Now this implies U bar plus V bar, okay, minus V bar what is here, what do we assume? U bar belongs to W1, not U bar belongs to W1, not V bar. Since U bar belongs to W1, minus U bar belongs to W1, and I am going to write here minus U bar. Okay, so here you can So u bar belongs to W1 minus u bar belongs to W1. Here also minus u bar. Okay, or I am writing this statement again. Minus u bar belongs to W1. So this implies u bar minus u bar plus v bar belongs to W1 by using associative. Okay, and by using commutative property. So what is u bar minus u bar? It is 0 bar plus v bar belongs to W1. So what this implies? This implies this implies v bar belongs to W1. But what is v bar? If you see here, what is v bar here? Okay, here you can observe this is okay. V bar belongs to what? W v bar belongs to what? W2. Okay, here you can check v bar is what? V bar belongs to W2, and we obtain here v bar belongs to W1. So by using definition of subset, how to show subset? Here you can check. This is the definition of subset. Okay, the definition of subset. If A is a subset of B, if X belongs to A is an element of B, then we can say that A is a subset of B. So by using same logic, what we can say here, since if V bar belongs to W2, then V bar belongs to W1, and therefore W2 is subset of W1, and therefore if W1 is not subset of W2, then W2 is a subset of W1, and hence proof. Conversely, now if W1 is subset of W2, then W1 union W2 is equal to W2, and since W2 is itself subspace, W2 is a subspace implies W1 union W2 is subspace. Now, and if W1 is a subset of W2, W2 is a subset of W1, then W1 union W2 is equal to W1. Okay, and W1 is a subspace given subspace, then W1 union W2 is also subspace, and hence the proof. Just I am writing here, hence the proof. Okay, I am going to discuss this. Why W1 union W2 is W1 is a subset of W2, then W1 union W2 is W2. So for example, say take set A is equal to 1 2, and take set B is equal to 1 2 3. Then clearly A is a subset of B. Then what is A union B? A union B is equal to 1 2 3, and which is equal to set B. So if A is a subset of B, then A union B is equal to B. Similarly, if B is a subset of A, then suppose if you take here, say now if you take A is equal to 1 2 3 and B is equal to 1 2, then clearly B is a subset of A. Okay, then here again A union B is equal to 1 2 3, and which is equal to what? A. So if B is a subset of A, then A union B is equal to A. Similarly, here you can check if W1 union W1 is a subset of W2, then W1 union W2 is equal to W2. But what is W2? Given. What is given? You can check here. Given. Where given? Okay, here given. What is W1 and W2 are subspaces of vector space V. So by using this logic, W2 is itself a subspace implies W1 union W2 is what? Subspace. Similarly here also.